Assalamu alaikum wa rahmatullahi wa barakatuh. Good day, gentlemen. Let me first start by sharing the screen. Okay. If you may recall, this is a makeup class. We're now in week 6, but in week 4, we missed a class. 1, because of poor Blackboard connection. 2, because of the holiday for the National Day. Okay, so we have, and then week 1, which we lost because the course was open late. Okay, so we have basically weeks to make up. Okay, so this is our lecture in which we will continue from where we started last week, and it is being recorded. So whether you join me now or you don't, you have to watch the video, and then if you have any question thereafter, you can always contact for more explanation. In our previous class, we're still in chapter 3, and we started discussing about the pressure measurements using manometers. Okay? A manometer is often shaped like the letter U. A device for measuring pressure by raising or lowering a column of liquid. So we're going to see several examples. Tanks, you can be water, you can have mercury, you can have, even more than one liquid, okay, at a time. So in this figure here, you have water flowing in a pipe, and you have the manometer attached to it. And what can you say about pressures at point 2 and 3? One thing if you look at 2 and 3, let me change the color. If you realize point 2 and 3 are on the same elevation, and we see fluid pressure at the same elevation is the same. Okay, the pressure of fluid at the same elevation is the same. It only varies with altitude, okay, or with elevation. As you go up, pressure decreases. As you go down, it increases. Okay, and here you have the manometer. At point 2 and 3, the pressures are equal because they are on the same elevation. Okay, what about if someone will ask you to write the pressure equation? The pressure equation in this case, because they are equal, you look at the two legs. Okay, at point 3 and 2, they are equal. So I start with point 2. This is very important. How to the pressure equation? I'll be taking you gradually from, simple problems to even some more complex ones, but the principle is the same. The basic principle here we'll be using is the fact that pressure for the points on the same elevation is equal. That is the general principle that we will be utilizing here. Now, if you look at point 2, let's start point 2, write the pressure equation. At the top of that YouTube, you have, it is open to the atmosphere. So it is open to the atmosphere, hence you have pressure acting. Okay, so you have P subscript ATM. Okay, so it is atmospheric pressure that is acting at the top. So what is the pressure acting on the right side of the tube? Okay, so you have first pressure due to the height, delta H, due to the height of the liquid, the manometer liquid, delta H, and pressure due to the atmosphere, which is acting on the surface of the liquid. Okay, so at point 2, pressure at point 2 is equal to the pressure due to the liquid above. Okay, because as you go up, you have the pressure exerted by the liquid column, this liquid column. Okay, delta H, and it's going to be height times the specific weight of the manometer liquid. So you have gamma m delta H, then plus the liquid plus the pressure at the top acting on the manometer liquid, which is P subscript ATM. That's the atmospheric pressure. Depending on what we are finding, if we want to find the gauge pressure, in this case, the atmospheric pressure is going to be 0, because for the gauge pressure, we set the atmospheric pressure to be our reference. And by reference, it means we make it 0. Okay, but this is the atmospheric pressure acting, and this is the pressure equation for the right leg. For the left leg, that is P3.3. Okay, so P3 in this case is going to be the pressure due to the height of the liquid up to 0.4, and yeah, if we consider it to be water that is flowing, because definitely the liquids are different. If you look at the color shade, I mean the thickness of the color, the first one is manometer liquid and the other one is probably water that is flowing. So let's assume it is water. So we will have pressure due to the height of the water column above 0.3, which is gamma W times L. L is the height of the water column, and then plus the pressure at 0.4, which is P4. Okay, so imagine we want to find P4. All we need to do is to say that the pressure at 0.2 is equal to pressure at 0.3. So in essence, what we are going to say is P2 is equal to P3. Okay, yeah. P2 is equal to P3. So in that case, we will have our equation generated. That is gamma M delta H plus P script ATM equal to gamma WL plus P4. And you can see here the only unknown P4. Okay, only unknown is P4, atmospheric pressure. You can use the exact value if you want to find the absolute pressure, whereas if you want the gauge pressure, you set the atmospheric pressure to be 0. L, delta H are values that should be known. Okay, so here you just make P for the subject of the formula. Is it clear? Okay, so now let's move on. The next slide. Okay, manometer's equation. Okay, this is exactly what I did in the previous slide. Okay, we write the manometer equation. Okay, here we are taking the atmospheric pressure to be 0. Okay, that's why you have this 0 here, meaning P4 here will give us gauge pressure, because we are referencing, we are taking reference from the atmospheric pressure, making it 0. Okay, so P4 here will be gauge pressure. Okay, and then generally P2 equal P1 plus. When you go down, you add the pressure because depth is increasing. When you go up, you subtract because the pressure is reducing. Okay, as you go down, pressure increases. As you go up, pressure decreases. When liquids and gases are both involved, this is very important because in some problems, as we are going to see, you have combination of both liquids and gases. So when they are both involved in a manometer problem, it is well within engineering accuracy to neglect the pressure changes due to the columns of gas. Why? Because we already mentioned when discussing about density in chapter 2 that the pressure of gas, or the unit weight of gas, is very, very small compared to that of liquid. And that is because of the density. Gas density is very small compared to density of liquid. I cited example previously. The density of air is about 1.2 kilogram per meter cube, while the density of water is 1,000 kilogram per meter cube. Just compare 1,000 and 1.2. That makes 1.2 to be so negligible. Okay, so much negligible. So that is why more often than not, because of the unit weight of liquid, generally, yeah, I cited example of water. You have other liquids whose density can be greater or even slightly less than water, but by and large, unit weight of liquids are far greater than the unit weight of gases. So more often than not, in situations, as we are going to see some of the examples that I'm going to discuss with you, when we have both liquids and gases, we more often than not neglect the pressure changes due to the columns of gases. Okay, because they don't usually affect our final answer, because the pressure they exert is very small compared to the pressure exerted by liquids. Now, the piezometer's equation, okay? The piezometer's equation, still P2 equal P1 plus, when you go down, you add, when you go up, you subtract. Okay? Here we have water flowing in a pipe, and then we have two pipes connected, and we have fluid B and A. Fluid be considered to be water, and then fluid B be considered to be, let me see. Yeah, someone is asking how many chapters. The exam is supposed to cover 3 chapters. Okay, so don't worry. We will 1 hour. I will know the question. I mean, even if it's one chapter, uh, it depends on the questions. One thing for certain is that the questions that will be asked will surely be solvable. You can solve it within 1 hour. So never mind. Just study very well. That's the most important thing. Okay. Let me continue. Okay. So explaining the piezometer's equation here, it is the concept. If you look at points, this point, if you look at this point, you shed it, let me call it point I, on the level, point I, but on the right side. Okay, so let's write the pressure expression for each of these points. Okay, just going by what we did before, I mean, it's very simple. For point I, that is the left side, all we need to do is that the pressure here is due to the height of the water, which is the height of the water up to point 1 is given by delta H and delta Y. Okay, so it will be uh, let me, okay, water delta H plus delta Y. This is the height of the water column, the entire unit weight of water. Okay, then plus the pressure at point 1, okay, of this point is P1. So it's equal to PI. Okay, so now let's write the pressure expression for PII for the right side of the egg. Okay, PII. Okay, so PII, the pressure here, we still begin from this bottom, from this elevation. Okay, so first we have the fluid B, whose height is up to delta H. So we have gamma B. Here we can write, instead, we can write gamma A, okay, because it is called fluid A, which can be water from the pipe. Here is, for this right hand side, we have gamma B times the height, which is H. Then we have the height up to point 2. Up to point 2, we have the same liquid, which is fluid A. But the height is, you have delta Y, then you have Z2 minus Z1. Okay, so we add, that is plus gamma B, gamma A now, not gamma, okay, sorry, gamma A, not gamma B, because gamma B, the fluid is up to delta H. That's why we use delta H for gamma B. Okay, for gamma A, the height of the fluid, of fluid A, is delta Y plus Z2 minus Z1. So use delta Y plus Z2 minus Z1. Okay, and then at point 2, we have P2, okay, plus P2. And then all we need to do, because they are at the same elevation, I and II, okay, they are the same elevation. So P is equal to PII, meaning the pressure at point I is equal to the pressure at point II, because they are on the same horizontal level. Okay, and if you equate them together, that is how you will arrive at this expression. Okay, equate PI to be equal to PII, then you will arrive at this long expression. Okay, so you can see here, like I mentioned, the bottom line, or the most important aspect, is having a certain horizontal level, the same horizontal level, and try to develop the pressure expression, for the right and the left sides, okay? And then you simplify to find whatever unknown that you need to find. For instance, here, if you want to find the pressure difference between point 1 and point 2, that is the pipeline, that is this point, that point. So all you need to do is to subtract and get P2 minus P1. Now, this expression for P2 can be simplified, can be rearranged in this, that is collecting like terms, P1 together with gamma A and Z1, okay, and then P2 together with gamma A and Z2, okay. So this we divide here in the next line, and then here we can divide throughout by gamma A, which is somehow common to most of the terms. So when we divide throughout by gamma, we obtain this expression. And this expression is simply given us in terms of piezometric head, okay? Because as we are going to see later, the piezometric head is simply P over gamma plus Z. That is elevation head plus pressure head, okay? Elevation head plus pressure head gives piezometric head, okay? So 1 over gamma A plus Z1, this is equal to H1, which is piezometric head, okay? And this is equal to H2, okay? So we now have H1 minus H2. So this gives the difference in the piezometric head between the 2 points, between point 1 here and point 2 there. Okay. We will solve an example to demonstrate the application of this simple equation. Okay. So change in piezometric head for pipe flow. Okay, let me quickly check something here. I think yeah, I think here I need to go back a little bit to yeah. Sorry, I just realized something that I jumped some slides. I shouldn't have started from these slides, but don't worry. I already explained this slide, so I'll just go back. This is where I was supposed to have started. That is about the piezometric head, and then we will continue with the manometric pressure, okay? Yeah, we are supposed to continue from this, okay? That is the hydrostatic equation, okay? But never mind, still our explanation of using the manometer to measure pressure is valid. So once we reach to those slides, we will build on that. I just realized that I mistakenly jumped the slides where I really explained the piezometric head where we derive some equations. So I just moved back to cover those few slides, and then we built on where we stopped now. Okay. So here we'll explain the hydrostatic equation. Okay. This section explains how to calculate the pressure for problems in which a fluid is in hydrostatic equilibrium. Okay. Hydrostatic equilibrium, so meaning, the fluid element is held by the pressure forces, okay, by the fluid pressure. The hydrostatic differential equation, which is there are two main results here, which is the hydrostatic differential equation, which is applied to problems in which density varies, okay, and the hydrostatic algebraic equation, which is applied to problems in which density is constant. I mentioned earlier when discussing about density that the density of liquid is constant. I mean, it doesn't really vary. Okay, so that's why we consider most, liquids as incompressible. But gases, their density are greatly affected by pressure application. Okay, while liquids, their densities, remains almost constant, irrespective of the pressure used. Okay, on the liquids. So gases are amenable, the density changes with pressure, while liquids have negligible, pressure has negligible impact on the densities of liquids. Okay. Now the hydrostatic differential equation. Let's see. Okay, it is showing. Like I said, I just moved back a little bit, some few slides before where I started, because I just realized that I mistakenly skipped some slides which introduced the piezometric equation, or the piezometric pressure head. Okay, so here to begin the derivation, you can visualize any region of static fluid, e.g. water behind a dam, and isolate a cylindrical body, and then sketch a free body diagram as shown. Okay, by free body diagram, you have to indicate all forces, active and reactive forces, acting on the fluid element. Here, the fluid element is cylindrical in nature, that is inclined at an angle. Okay, and we apply the force equilibrium in the L direction. Okay, and the weight will be acting vertically downward because of the angle of inclination alpha. This is also alpha. Okay, so you have pressure, force acting on this face. Okay, pressure is compressed, so is acting like to compress the fluid element. Okay, as you move at this delta L, you have P plus delta P, so meaning the pressure is expected to rise in the direction of L. Okay, so that's why here you have delta P. You have the same area, the same cross-sectional area, delta A. Okay, and the weight of the liquid, weight is simply mass times acceleration due to gravity, and mass is simply density times volume, then times G. Okay, rho G is gamma, so gamma times volume, and the volume of the cylinder is going to be the cross-sectional area times the length. So that's why you have gamma delta A delta L. Okay, so this is the weight of the element. And now we'll apply resolution forces. Okay, we sum forces along L, okay, along the L direction. And when we do that, when we sum the forces, we have the pressure forces, okay, and then we have the weight also, which can be resolved. Okay? The weight can be resolved along L direction. Okay, this is the L direction. So here we have the pressure force minus the weight equals 0. So hydrostatic condition prevails because the weight of the fluid element is supported only by the pressure forces. Okay. Okay. So now here you have, pressure force, this minus the other pressure force at the other end, and this is the resolution of the along L direction. That's why you have sine alpha. Okay, you have sine alpha. And we can simplify this equation by dividing by the volume, delta L, delta A. When we divide by delta L, delta A, which is the volume of the fluid element, we will be left with delta P, delta L equal minus gamma sine alpha. And from the figure, sine of the angle is simply delta Z over delta L, because sine is opposite over hypotenuse. Okay? And combining the previous two equations and letting delta Z approach 0. Okay? Here you can delta Z. So if it approaches 0, so what will happen? That the angle is going to be very small. Okay? When delta Z approaches 0, so you now have the limit. The limit as delta Z approaches 0 to be delta P over delta Z, which is equal to minus gamma. Okay, this is equal to minus gamma. Okay, as delta Z approaches 0. So this is delta Z. Okay, this is delta Z. Because sine is opposite over hypotenuse. Okay. So now the final result will now be dP dZ equal minus gamma, which is the hydrostatic pressure equation. Okay. Don't forget gamma is equal to rho G. Okay. So when you have rho to be variable, when the density varies, you have dP to be equal to minus rho G dZ. Okay. And if you want to find the pressure, you now integrate. So you now express the density if it is varying with Z, with elevation. You now express, you give the function or the equation relating the pressure or how density varies with Z. That's the equation showing the variation of the density with Z, and you have to integrate so that the final that is for variable density. Okay, and the minus, like I explained before, if you remember, is because of the fact that when you go down, when Z reduces, pressure increases. When Z increases, pressure reduces. So that's why you have this negative sign. Okay, so this can be simplified to give us P equal to gamma Z. Okay, and gamma is what? Rho G. Z is just height, which is elevation. So you have P to be equal to rho GH. Okay, so this is like the simplification of the differential, the hydrostatic pressure equation. P equal rho GH. G is the height. Okay, is the height of the liquid column. G is the density. G is the acceleration due to gravity, which is also constant. Okay, usually constant on the surface of the Earth. And then rho is density. Now, still on the to derive down the hydrostatic algebraic equation, when the density is constant, okay, we call it HE, hydrostatic equation. To derive the equation, we begin by integrating 3.7, okay, for the case of constant density. You know, what are we integrating? dP dZ equal minus gamma. So this is what we are integrating, okay? So here we'll have dP equal minus gamma dZ. For constant density, so gamma will go out because it is constant, okay? And then for integration, this becomes P, and then this is minus gamma Z plus constant. Okay, so it's going to be P equal minus gamma Z plus constant C. Okay, so when you take this to the other side, you will have plus gamma Z equals constant, okay, which is exactly what I have here. P plus gamma z equal Pz. Pz is constant, is the constant of integration, okay, and z here is the elevation, the vertical distance above a fixed horizontal reference plane called a datum, okay, and here that constant of integration is called the piezometric pressure, okay, that constant of integration Pz, okay, is called the piezometric pressure. Okay, and here we can divide throughout by another constant, which is the unit weight, okay, and we will have Pz over gamma equal to uh, that is the piezometric pressure over gamma to be equal to P over gamma plus Z, okay, and again dividing a constant with another constant, you have another constant, okay, so that's why this is equal to H, which is the piezometric head. This is piezometric pressure, and this piezometric head, meaning the piezometric head is the piezometric pressure, okay, divided by gamma. Very simple, okay, and this is all constant, where H is the piezometric head. So because H is constant, it can be, since H is constant, meaning it's the same, for this P over gamma plus Z is a constant, it's always constant. So when you tell me 2 points, that value should remain the same for those 2 points, meaning P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. So this is referring to the piezometric head for 2 different points. So the piezometric head for any point of a static fluid is always constant. We will also expatiate more on this, okay? Where the subscripts 1 and 2 identify any 2 points in a static fluid of constant density, very important. The density here is considered to be constant. That is why when integrating here, we remove the unit weight of water outside the integral because we are considering the unit weight to be constant. When the unit weight is considered constant, it means G is constant, rho is constant because unit weight is equal to rho G. Okay, this we know before. Okay. So now multiplying by gamma, we go back to the previous equation, which is this one, okay? So we can also express it P1 plus gamma Z1 equal P2 plus gamma Z2, okay? And here we can like bring this here to have P2 minus P1, which is the change in pressure, okay? And Z2 minus Z1 to use delta Z, okay? So this will simplify us to go back to the previous equation that we started with, which is this one, dp dz equal minus gamma. So this is now in algebraic form, delta p equal minus gamma delta z. So we just like move back to the equation that we started with, okay? And I already explained that the negative sign here is showing that the pressure in a static fluid increases linearly with depth, okay? It increases linearly with depth. The fact that this is just minus gamma, which is constant, so that is, it means it is linear, okay? And if you look at this figure, this is like a container containing water, okay? The pressure at the top is atmospheric, which we normally take it to be the reference for the gauge, okay, which is 0. But as you go deeper down, the pressure increases. That's why you have P gauge, okay? So the gauge pressure increases. If you don't, if you want to use the absolute pressure, it means at the top is going to be some value here, okay, and then when you go deeper down, it will increase. So this from here to here is now accounting for the constant atmospheric pressure acting. And then as you go deeper down, the pressure increases because of the weight of the fluid element that are increasing with depth. I mentioned before that pressure is simply, the weight of the fluid above. I mean, just imagine you carrying heavy load. When you carry 1 kg, it's not the same as when you carry 10 kg or 20 kg. The more the weight, the more the pressure you feel in your palm, I mean, on your palm, on your head, and all that. Okay. So this is the piezometric pressure as well as the piezometric head, which I was explaining in the slides that I started with. Okay. But just I realized that I mistakenly skipped this introductory part. Now, still on the hydrostatic algebraic equation, an easier equation to remember and apply between any 2 points in the same fluid under hydrostatic condition is delta P, that's the change in pressure, is equal to P2 minus P1. Okay, P2 minus P1, which is equal to minus rho G delta Z. Okay, rho G is gamma. Okay, so we are just saying delta P equal minus gamma delta Z, which can be interpreted, because P2 here is the pressure above, okay, and P1 is the pressure below, which is higher, okay, which is higher. So with this P1, what is P1? P1 is simply P1 is simply equal to P2 plus gamma delta Z. Okay. Okay. So because P1 is the one below. Okay. Let's say at this point. Okay. So the pressure below is equal to the pressure above. Okay. Which is like the atmospheric pressure. Okay. Plus the height of the column, the fluid column. In this case, the height of the water above. Okay. So the pressure below is equal to the atmospheric pressure plus rho GH, because this is just rho GH. Okay, and because we add atmospheric pressure here, if we remove it, it means this is absolute pressure. So this is just gauge pressure plus and rho GH. If this atmosphere, then the additional pressure rho GH is gauge. Okay, which is the pressure above atmospheric. Gauge pressure is the pressure above atmospheric. Okay, so the pressure P is just equal to P atmospheric plus rho GH. Okay, so this rho GH is the gauge pressure. Okay, so if we want to find the gauge pressure, we don't need to include the atmospheric pressure, because the atmospheric pressure will be assigned a value of 0, because it is the reference for the gauge pressure. Okay, and for a fluid, the vertical distance delta Z is sometimes used as a measure of pressure. Okay, the vertical distance delta Z, and it is called the pressure head. This we just finished explaining. Okay, the pressure head, and then we have the can see we have pressure head and we have piezometric head. Okay, the pressure is the sum of the piezometric head is the sum of the pressure head and elevation head. Okay, the pressure head is the sum of the elevation head plus the pressure head. Okay, so for a fluid, the vertical distance is sometimes called the pressure head. Okay, yeah, here we have H, okay, which is the piezometric head, okay, which is the sum of the pressure head. This is also the vertical distance, okay, and this elevation head, okay. And if we take the above point to be at the free surface, this I just mentioned, then we have atmospheric pressure acting, okay, and then the pressure at a depth below the free surface, you add atmospheric pressure, unless you gauge. If you call it gauge, you ignore the atmospheric pressure because it is the reference which will be set to 0. Pressure in a fluid at rest is independent of the shape or cross section of the container. Okay, it is independent of the shape or cross section of the container as long as it is at rest. Okay, what it only depends is on the distance. Okay, the elevation. It changes with the vertical distance, that is with elevation, but remains constant in other directions. In other horizontal directions, it remains constant. It changes only with vertical direction. Okay, therefore the pressure is the same at all points on a horizontal plane given fluid. This we proved, if you remember, we proved we look at the pressure acting on a fluid element, and we realize it's the same at all points on the same elevation. Yeah, on the same elevation, the pressure acting on a fluid element is the same, irrespective of the direction. And there we confirmed, or we inferred that the pressure is the same at all points on a horizontal plane. It only varies with elevation. When the vertical distance changes, if you go deeper down, the pressure is higher. If you go up, then the pressure is less. So still on the hydrostatic equation, okay, is given by these equations. The piezometric head is given by P of gamma plus Z, and the piezometric pressure is given by P plus gamma Z. And the piezometric head, like I mentioned, is given by the piezometric pressure divided by gamma. Okay, the piezometric head is given by the piezometric pressure divided by gamma. So this is very, very important. Okay, the piezometric head given by the piezometric pressure divided by gamma. And the hydrostatic equation is valid for any constant density fluid in hydrostatic equilibrium. And you should, to calculate the piezometric head or piezometric pressure, an engineer identifies a specific location in a body of fluid and then uses the value pressure and elevation at that location. Okay, piezometric head and pressure are related by piezometric head and pressure are related by. I already wrote it there. Okay? The piezometric head and piezometric pressure. This is the relationship. H is equal to Pz over gamma. Okay, this is the relationship between piezometric head and piezometric pressure. So we derive this, that the hydrostatic equation, okay, the piezometric pressure is the same for all points. Okay, so P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. This is the hydrostatic equation, and this is the same at all points. Okay, and this we said is equal to the piezometric head. Okay, and then this is the piezometric, the piezometric pressure Pz, and Hz is the piezometric head. Okay, no, this is the head. Sorry, the piezometric head. Because this is in form of head, the piezometric pressure will be P1 plus gamma Z1. Okay, so this is the piezometric pressure. Okay, P. Okay. Now we said for different points, point 1 and 2, they have the same piezometric head. The equation implies that piezometric pressure is equal for the same fluid regardless of the elevation. Regardless of the elevation, the piezometric pressure is the same. Yeah, someone will say, but we mentioned that pressure increases with elevation. Yes, it does increase, but the piezometric pressure, which is the sum of the elevation head and the pressure head, when you add them up, the pressure, the piezometric head remains same. We'll explain this with this example. Okay. Here is saying, is the piezometric head equal in A and B? A, this is A, this is B. Yes, they are equal because it is the same fluid. Okay, it is the same fluid. Okay, how do we find the piezometric pressure here? Okay, the piezometric pressure for A. Okay, no, the piezometric head for point A is going to be pressure at A over gamma plus ZA. Okay, that is the pressure acting of the liquid acting this height. Okay, plus the elevation head. Okay, which is ZA. So when it's the same liquid, okay, and of course you have the weight of the oil in here, okay. So this will add up to give us, this will give the total weight of fluid at this point, which will be taken care of by PA over gamma, and this is ZA, okay. When you move to B, this is Z. So you add the total weight of fluid for the oil and the water, okay. So when you add this up, they will still give you this level, okay. They will still give you this level, okay, and that is the piezometric head, okay. So the piezometric head here, H, is the total height from the bottom to the top, okay. So whether you are considering this point A or point B, it remains the same. Now, what about point A and D? This is point A and D are in different liquids, okay. They are in different liquids. You remember we mentioned that the condition for using the hydrostatic equation is that the density must be constant. Density must be constant. In this case, density is not constant. This is oil, this is water, two different fluids. Okay, the oil density is definitely, as it is shown, floating on top of water, it is less dense than water. Okay, so in this case, the piezometric height are not the same because the density is not the same for oil and water. Okay, the same thing when you consider C and D. C is in water, D is in oil. So the piezometric head is not the same because the densities of the two fluids are different. The same thing D and F. No, D is the same fluid, so it has the same piezometric head. Okay, they have the same piezometric head because the 2 points are within the same fluid, so the density here is the same. Okay, the density of the fluid element here is the same. Okay, this is very, very important. So we mentioned that the piezometric head is given by the piezometric, so the piezometric pressure is given by the piezometric head times gamma. Okay, piezometric head times gamma, and this can be simplified to, because gamma is rho g, then we have H. So H is the piezometric head. Okay, H is the piezometric head, which consists of the elevation head and the pressure head. Okay, the elevation head and the pressure head. So this is the simple explanation of what I, in the previous slide, giving all the explanation, okay, of the different points, comparing different points within the same liquid, A, B, and C. They have the same piezometric pressure, okay, and they have the same pressure piezometric head, while D, E, F, they also have the same, but not when you mix between the points within the oil and some points within water, because in that case, they will not have the same piezometric head, neither will they have the same piezometric pressure, because the two densities are different. Okay, the two densities are different. And this a table summarizing the hydrostatic equations, the working equations, and some of the assumptions. Okay, delta P equal gamma delta Z, and when you integrate, okay, you arrive at the piezometric pressure, which we can also get the piezometric head, okay, which we can simplify to give us the generalized P equal rho GH, okay, where H in this case is the piezometric. Now, let's look at what is called fluid interface rule. Okay, The fluid interface rule states that for a planar interface, example of this interface fluid A and B, we have water, okay, here is water and it can be air, okay. So at the interface here, when you're considering equilibrium, you have the pressure force acting due to the fluid 2, which is P2A, and you have, because you are considering the same area, and here you have P1A. Okay, so when you look at the equilibrium condition of this fluid element, the two forces have to be equal. So P2A equal P1A. So P1 equal P2. So what are we saying is that the pressure acting at the interface is the same. Okay, pressure is constant across the interface. That is P1 is equal to P2 at the interface. Okay, because the fluid interface is not moving. So the net force acting, it is in static equilibrium. The net force acting is 0. Okay, and here we select a very small, infinitesimally thin system such that the weight can be neglected. Okay, so here we are only considering the pressure forces acting due to fluid 2 and fluid 1 on the element. Okay, we are neglecting the weight of the selected element. Okay, so P1 equals P2. And that is why, here, if it is air, atmospheric pressure acting, isn't it? And at this point, we usually take the value of the pressure to be atmospheric pressure acting on the surface of the liquid. Okay. Now, gas pressure change rule. The gas pressure change rule states that the hydrostatic pressure change for a gas can be usually neglected. Okay. And I mentioned the hydrostatic pressure for a gas can be usually neglected. Why? Because the density of the gas, uh, the density of the gas remains almost constant with elevation. Okay, and the density is very small. The density is very small. So for some small change in elevation, the pressure remains the same. The hydrostatic pressure change in a gas for 1 meter change in elevation is given by delta P over delta Z equal rho G. Rho is very small for gas. Okay, it is very small for gas. So for small elevation change, the hydrostatic pressure change, is very negligible. Okay, for instance, the pressure change in air at room conditions is about 12 pascals per meter. Okay, 12 pascals per meter. And remember, the atmospheric pressure is 101 kilopascal. It's 101 kilopascal. So example here we have, it shows how to find the pressure by applying the idea of constant piezometric head to a problem involving several fluids. Notice the application of the fluid interface rule. So here you have, a room. It can be your own room. At the bottom, the atmospheric pressure is 1.006 atmosphere. The height of the room is 5 meters. Okay, and there is air inside. So at the top, atmospheric pressure, which is just 1 atmosphere. So you can see that as you go higher, the pressure has reduced. After like for a depth of 5 meters, the pressure reduced by 0.006 atmosphere, which is very, very small. Okay, and negligible for all practical purposes. Okay. So that is why the pressure one for, let's say, the atmospheric pressure is considered constant on the surface of the earth, but when you go some kilometers, let's say 10 kilometers above the earth's surface, the atmospheric pressure may reduce to, let's say, 0.8 atmosphere, okay, which is still not so much different from 1 atmosphere. Okay, but as you go higher, it tends to decrease up to a point where you reach and where you have almost vacuum. By vacuum, mean you don't have air, zero air is existing there. Okay, so the pressure change with elevation for gas is negligible. That is the bottom line. Now, attention quiz. What is the pressure at a depth of 10 meter in the tank? Okay. What is the pressure at a depth of 10 meter in the tank? So this is the elevation 75, 10 meter into the tank, 0.1, 0.2. So we want to find the pressure here. Okay. At this point, what is going to be the pressure? Okay. The pressure at 10 meter, simply due to the height, okay, gamma h. You have 10 meter times gamma 9810, okay, which is 9810, okay, which is going to be Pascal. In kilopascal, you have 98 kilopascal. So this is the pressure due to the height of the water, okay. And then, of course, if you want to find the piezometric pressure head, the piezometric pressure Hz for this same point is definitely equal to the elevation here, which is simply 75 meters. Because if I said the piezometric pressure at point 2 is going to be the elevation, which is 75 minus 10, 65 meters, then plus the pressure due to this one, okay? So it is going to be the elevation, which is 65 meters, plus the pressure due to this 10 meter, okay? Due to this 10 meter of water, okay, at this point, which is, if I am to use the head, is 10, okay, so it's 75 meters, okay? Someone may say he wants to use P1 or P2 over gamma. You will arrive at the same value, because what you are doing, you dividing this by gamma, and gamma is 9810. Okay, so it's going to cancel out and you will be left with 10. Okay, so it's still going to take you back to the total height, which is 75. Now, this is another example which says oil with a specific gravity of 0.8 forms a layer 0.9 deep in an open tank that is otherwise filled with water. You have water to a depth of 2.1 and oil to a depth of 0.9. Okay, the total depth of water and oil is 3 meters. 0.9 plus 2.13 meters. What is the gauge pressure at the bottom of the tank? What is the gauge pressure? Meaning, in this case, atmospheric pressure is the reference, so it is 0. So what is the gauge pressure at the bottom of the tank? Okay, this is what we want to find. So here you have P1, P2, P3. Okay, so what is the gauge pressure at the bottom of the tank? So we need to find P2 by applying hydrostatic equation and equate the pressures across oil and water interface. Okay, and equate the pressures across oil water interface, and we find P3 by applying the hydrostatic equation. Okay, so we apply the hydrostatic equation between point 1 and 2. Okay, point 1 and 2. This is P1 is atmospheric because it's at the top of the oil. It's air. Air is acting on the top of the oil. So hence, this is P1, which is atmospheric. That's why it is 0. Okay. And the point, this is the reference atom. Okay, reference point. So that's why we have Z1 to be 3 meters. Okay, so 3 meters. And then for P2, this is P2. We want to find the pressure, so we don't know what the pressure is over gamma. Gamma is rho g. This is the density. This is the density of the oil. okay, times G, okay, although here provided in kilonewton, 0.8 times G, okay, plus Z, okay, Z is 2.1. So 2 is given as 7 kilopascal. And then for the oil-water interface, which is here, we now consider the pressure for the oil at this interface is called the pressure for the water at this interface, 7 kilopascal. Now the hydrostatic equation to find P3, now to find P3, we apply the same formula, the same piezometric pressure, okay? At this point, we use this formula, P2 over gamma water plus Z2, okay, is equal to P3 over gamma water plus Z3, okay, plus Z3. So now P2 is equal to this value, okay, over gamma for the specific weight plus Z2, okay, which is the elevation, okay, for the water column, 2.1 meter, okay. At the bottom, which is our reference point, Z3 is going to be 0, okay. So this is our P3, okay. So here the only unknown is P3, which we can make the subject of the formula, and we have to write, okay, because we equated the atmospheric pressure to be 0. So the final value of the pressure we are going to obtain here is gauge. If we ask for the absolute pressure, if we say we want to find the absolute pressure, all we need to do now is to add atmospheric pressure here. Simple. P atmosphere. So this will now give us 1 plus 27.7. Okay, and this will be absolute pressure. So what have we done basically? We use the concept of the piezometric head. Okay, first we look at 1 and 2, okay, to find the P2. Okay, and then we looked at point 3, 2, and 3 to find P3. Okay, very simple. Okay. So validation here, it says because oil is less dense than water, the answer should be slightly smaller than the pressure. The answer should be slightly smaller than the pressure corresponding to a water column of 3 meter. Okay, should be slightly smaller than the pressure corresponding to a water column of 3 meter. Because if you have water throughout, water is denser than this oil because the density of the oil is 0.8. So it should be slightly smaller. Okay, this value should be slightly smaller than if it were to be filled with water throughout. Okay. Because a water column should produce, a 3 meter water column should produce a pressure of about 30 kilopascal. Okay. So whereas this one produce a pressure of 27.7 because of the presence of the oil, because oil is less dense than water. This oil, you may have another oil that is denser than water, like crude oil. Okay, that one is denser than water. Still on the hydrostatic pressure, okay, if we want to find the pressure at point B, all we need to do is to use GH, okay, the height of the water column times rho G. The pressure variation with elevation. This we explained also in hydrostatic condition. Fluid particles at the same elevation experience equal amount of pressure if you have the same fluid, if it is within the same fluid. Okay, If it is within the same fluid, they experience at the same elevation, they experience equal amount of pressure. And pressure on fluid particles varies as the elevation of the fluid particles varies. So point C and D, they have the same pressure, which is C is different from A, and A is having higher pressure than point C because it is deeper down, okay? But they all have the same piezometric pressure because the piezometric pressure is taking care of the pressure head and the elevation head, okay? So the piezometric pressure is at the top of the water for each of the particles, okay? When you sum it up. So pressure variation with elevation. I started mentioning in, when we have a room of 5 meters, the pressure at the bottom 1.006 atmosphere, and at the top is 1 atmosphere. So it varies slightly with elevation, okay? But this is because the elevation is so small, just 5 meters. What about when you go so many kilometers into the atmosphere? The atmosphere is about 1,000 kilometer thick. 1,000 kilometer thick. Okay, when you fly, in a passenger jet plane, you travel at almost about 10,000 feet, 10,000 meters above sea level. That's about 10 kilometer, times 10, 11, even 12 kilometers. Okay, but the total thickness of the atmosphere is about 1,000. Okay, and it's divided into 5 layers. In the troposphere, which is defined as the layer between sea level and 13.7 kilometer. So that is the first layer, troposphere, from the sea level up to 13.7 kilometer, which is usually the layer within which our planes cruise. Okay, so the temperature decreases linearly with increasing elevation at a lapse rate of 5.7 Kelvin per kilometer. That's why as you go higher in the troposphere, the cooler it becomes. It becomes cooler. Okay, and the lapse rate is 5.7 Kelvin per kilometer. Okay, and this is represented in this figure here. You can see, the temperature decreases by 5.87, okay, linearly in the troposphere. Okay, where the altitude up to 13.37. Okay, it decreases linear approximation. Okay, this is the troposphere. Okay, temperature decreases. This is about like 20, 21, so it decreases up to maybe 60 thereabout. So that's why in the plane, when you see the temperature, they will tell you it's about minus 50, minus 45, minus 50 degrees Celsius. So extremely cold. Okay, and then this you after the troposphere you have the stratosphere, okay, which is the layer that begins at the top of the troposphere and extends up to 50 kilometers, okay, up to 50 kilometers. In the stratosphere, the temperature increases with altitude, which is this other leg, okay, it increases with altitude. It slightly increases with altitude up to about 50 kilometers, okay. Don't forget the atmosphere has length, uh, thickness of about 1,000 kilometers. The ozone layer is found within the stratosphere. You remember the ozone layer when we talk about climate change, the layer that is absorbing the ultraviolet radiation, I mean, is trapping the harmful rays from reaching to the surface of the earth, which is the ozone layer. But because of our practices, because of the greenhouse gases that we are emitting into the atmosphere, the carbon dioxide, methane, they are they are depleting and reducing the thickness of the ozone layer. And that is why we are having, the temperature of the earth is gradually warming up, gradually warming up. That is the global warming. So the earth is gradually become warmer and warmer and warmer. Okay, and that is having a lot of impacts on our weather condition, on a lot of other factors. Okay, a lot of our lives, a lot of floods, a lot of high temperatures, and what have you. So the ozone layer is found within the stratosphere between 15 to 30 kilometers. Okay, between 15 to 30 kilometers. You can see this is 15 to 30 kilometers. So the ozone layer lies within this range. Okay, and the thickness of the ozone layer varies by the season and also by latitude. Okay, atmospheric pressure changes from 101 at sea level to 89, 79, 54, and 5.3 at altitudes of 1,000, 2,000, 10, 5,000, 10,000, and 20,000 meters respectively. Meaning at 20 kilometers above sea level, what is the pressure? 5.3. So at 20, at this point, the atmospheric pressure is just 5.3, very small. At sea level here, at sea level, which is at zero altitude, is 101 kilopascal. Okay, if we move up to 1,000, 5 kilometers, 5 kilometers is about 54. Okay, 5 is about 54 kilopascal. So the atmospheric pressure reduces at you as you go up, like I said, up to a point where you reach almost absolute vacuum. Okay. Now pressure measurements. Pressure measurements, we can use barometer, you can use Bourdon gauge, Bourdon tube gauge, you can use piezometer, we can use manometer. Okay. When I started explaining the piezometer, the manometer. Okay. So some conversion factors between different units of pressure. Okay, I explained that 1 atmosphere is approximately equal to 1 bar. Okay, which is approximately equal to kilogram force per centimeter square as well. Okay, so these are the various units of pressure, both the SI and the non-SI. The SI unit of pressure is Pascal or Newton per square meter. Okay, this is the SI unit. Okay, this is Torricelli. Okay, 1 atmosphere is 760 Torricelli, 760 or 760 millimeter of mercury. Now, okay, still on the pressure measurement. Here we look at barometer. Okay, the barometer is an instrument used to measure atmospheric pressure. So that's why sometimes we refer to atmospheric pressure as barometric pressure. Okay, it's simply a tube in which you fill mercury or water and invert it, put it in a container containing either mercury or water, as the case may be. So here you have the tube. When you invert it, this is vacuum, and this mercury column is supported because of the atmospheric pressure, because you are acting here. Okay, and definitely given the interface rule, okay, the pressure at the interface here within the mercury is also equal to atmospheric pressure. Okay, so that's why here we have atmospheric pressure acting onward. Is the pressure within the liquid, okay? Because of the interface rule, this is P atmospheric, and it's controlled also by P atmospheric because it is a static fluid, okay? And you have this height of the mercury column being supported. This is the weight of the mercury column, rho g h a, okay? That is the pressure times the area, okay? Because this is vacuum, the pressure here is 0. So you have the atmospheric pressure supporting the weight, okay? So it is hydrostatic. The system is hydrostatic. So the pressure, the vacuum pressure is very small, 2.4 times 10 to the power minus 6 atmosphere at 20 degrees, the vapor pressure. Okay, so this is very, very small compared to 1 atmosphere, which is the atmospheric pressure. 1 compared to 2.4 times 10 to the power minus 6. So definitely we can neglect the vapor pressure. Okay, so when we look at the equilibrium of the fluid element here, the atmospheric pressure is equal to the pressure due to the mercury column, which is gamma H, then plus the vapor pressure acting, okay, which is approximately 0 compared to the atmospheric pressure because it's very small, okay. So the atmospheric pressure is given by the height of the mercury column, okay. At 20 degrees, 101 kilopascal, dry air has a density of 1.2 kilogram per meter cube, very small, okay. This height, this we use to measure the atmospheric pressure. Like I said, this height H for mercury is always equal to 760 millimeter or 0.76 meter, okay, irrespective of the size of the tube used. You can see the cross section area A1 is greater than A2, greater than A3. But when you invert it and place it inside a mercury, they all rise to the same level because the atmospheric pressure acting is constant. Okay? Because the atmospheric pressure acting is constant. That is why it is used to measure the atmospheric pressure. And that's why we express atmospheric pressure using the height of the mercury column. That's 760 millimeter of mercury. Because when you invert it, the atmospheric pressure will push it up to that height. Okay, and that height is irrespective of the cross-section area of the tube used. Okay, it will rise to this height. Like I mentioned, if you use water, because water is denser than mercury, it will rise to 10.33 meter, which is way higher, about 14 times higher than that of mercury. And this is solely because of the density, because the density of mercury is about 14 times higher than the density of water. So that water will rise 14 times to a higher level. The same atmospheric pressure, one atmosphere will raise mercury 760 millimeter, but if it were to be water, the same one atmosphere will raise water to a height to a height of 10.33 meter of water. Okay, and this is solely because of the density. When you factor in the density of mercury is 14 times, about 14 times higher than the density of water. The same thing, the height to which water will rise is about 14 times higher than the height to which mercury will rise, because mercury is denser than water. Okay. So this is it. You have the vapor pressure for mercury, and you have column of mercury rises to a height h, and this atmospheric pressure, which is pushing, okay, which pushes down, okay, on the mercury, okay, the resulting effect of which the mercury rises up in the column. Now, concept quiz. Measuring the atmospheric pressure, the barometric heights for mercury and water are 76 centimeter, which is 760 millimeter or 0.76 meter, and 10.33 respectively. Why are the heights different? Explain. I just finished explaining. The heights are different because mercury, if you take, for instance, 10.33 or 0.7, will approximately equal to 14. Okay, and this is because the same thing when you take the density of mercury over density of water, it's also approximately equal to 14. Okay, density of mercury is 13,500 kilogram per meter cube. That of water is about 1,000. Okay, so dense mercury is higher, is denser than water. So for that atmospheric pressure, which is constant, which is 1 atmosphere, if it is mercury, it will push it up to this. If it is water, it will be 14 times because it is denser than water by 14 times. So it will push it up to 10.3 meter, 10.33 meter, which is very high. Okay? And that is solely because of the density of water. If it were to be another liquid whose density is between water and mercury, it will be raised to the same. If you have another liquid, let's say mercury, and let's say oil, I don't know the density. Okay, so when you divide whatever you get here, you just multiply it, the factor value you get, with the height of mercury, and that will now give you exactly the height to which it will be raised. Like get 3, you just multiply 14, this 14 by 0.76, and water will be raised to 10.33, okay, which is about 14 to 0.76. Now the other question is saying, why does cooking takes longer at high altitudes? Okay, I explained it before when explaining the Himalaya and the Jeddah scenario. Definitely, when we go back to this, you can see the atmospheric pressure decreases with height. Let's say you are at about 10 kilometers above sea level. What is the pressure? The pressure is just 26.5 kilopascal. Okay, the pressure is just 26.5 kilopascal, meaning at this point, water cannot reach 100 degrees Celsius. Okay, it will not reach 100 degrees Celsius before it begins to boil. Okay, once the vapor pressure reaches 26.5, it will begin to boil. You can imagine water at 26. I cannot predict. Maybe we will have to go back to chapter 2 under vapor pressure to check what the table. Let me quickly check to see the uh, temperature of water at this pressure. Okay, under the vapor pressure of chapter 2. Okay, when you have the vapor pressure to be 26.5, yeah, it's about 65, thereabout, 65 degrees Celsius, about 65 degree Celsius. Yeah, about 65 degrees Celsius. So it means at 10 kilometers above sea level, water will boil at about 65 degrees Celsius. 65 is not as hot as 100 degrees Celsius. So definitely, if you heat above 65, all water will vaporize and it will disappear and you will have nothing to cook with. Okay, so you have to maintain temperature somewhere below 65, let's say around 60, to avoid the vaporization of the water into vapor. Okay, and 60 degrees cannot be compared to, let's say, 95 degrees Celsius at sea level, when atmospheric pressure is 1 atmosphere. At sea level is 1 atmosphere. This is at 10 kilometers above sea level. So you can heat the water, you can cook with water at this temperature, 60 degrees Celsius. So definitely it will take longer before your food gets cooked. Okay, because the temperature is lower, and unfortunately, because of the pressure, you cannot heat cook. You cannot heat the water above 65. 65 is not the boiling point of water. Is it clear? So now this is the explanation. This okay, and then why is the density of air affected at high altitudes? Explain. Why is the density of air affected at high altitudes? Explain. Yeah, the density of air is affected at high altitudes. When you go up, the density is affected because of the low pressure. Okay, low atmospheric pressure, it means low density. The density will be less because density is all about pressure. Okay, if you have less amount of matter, less amount of fluid, then the density exerted, because density is mass over volume. So the mass has reduced. If the mass has reduced, definitely the density will reduce. When you go higher, up to the troposphere, in the troposphere, you can see as you go higher, the atmospheric pressure reduces. Okay, it keeps on reducing up till when, because the atmosphere is about 1,000 kilometers thick, and as you go higher, the amount of air reduces. It reduces because the atmospheric pressure reduces, thereby what that means is that the amount of air, the mass of air acting reduce as you go higher. Okay, So that is why the density will definitely be affected, because density, as we defined before, is simply mass divided by volume. So if the mass decreases, definitely density exerted will decrease if you have constant volume. Okay. Now, pressure measurement. We discussed about the barometer, okay, which is used for measuring the atmospheric pressure, and then we have the wooden tube gauge. Okay, this is what used to measure pressure by sensing the deflection of a coiled tube. At atmospheric pressure, the pressure is calibrated to zero. This is similar to even what we use to measure the pressure in our tires. Okay, I have it in my car. I don't know if you do. Okay, you have to put it, to the valve. Okay, so that it reads the pressure. At atmospheric pressure, without connecting it to your tire, it reads zero, because it is gauge. It measures the gauge pressure. That's the pressure above atmosphere. Okay, it's graduated sometimes in PSI and also in bar. For my tire, I think is the minimum pressure needed is 2.7 bars. Okay, so this is the Boudin tube gauge. Uh, Pressure measurement using the Boudin tube gauge has advantages as well as disadvantages. The advantages are it is easy to install, it is low cost and reliable, and is available in different pressure range. The disadvantages are dynamic pressure, not read it accurately. Dynamic in the sense that the pressure changes with time. Okay, and then it will have it has low accuracy, and it is vulnerable to extreme pressures. When the pressures are very, very high, it will not be able to read correctly. Now, another instrument for measuring the pressure is the piezometer, okay, which is a vertical tube, usually transparent, in which a liquid rises in response to a positive gauge pressure. Positive, we say gauge pressure, that's the above atmospheric pressure, okay, which is usually transparent tube, which is vertical, in which a liquid rises in response to a positive gauge pressure. Here at the top of the tube, you have atmospheric pressure acting. Okay, here you have water, probably water flowing in it, and this is the height. So to find the pressure in the tube, all you need to do is to, when you have the gauge, the height to which it rises, okay, now use the piezometric height and multiply by the unit weight to get the pressure acting in the pipeline at this point. Okay, because the pressure will push it. I mean, the pressure here is what is responsible for pushing it up. Okay, so it's dependent on the height to which water or the fluid rises in the piezometer. You now use it to find the pressure acting. So the piezometer has also its advantages and disadvantages. It is very simple and it gives direct measurement, no need for calibration, and it is accurate. And the disadvantages is that it cannot be used for measuring pressure in a gas, because of course gas will disappear, because piezometer is an open tube. Okay, so gas, if you don't close it, particles are far apart from each other, so they will just disappear. They will serve as a leaking point. Okay, and it's limited to low pressures. Why is it limited to low pressures? Because the pressure is proportional to the height. Okay, because you use P equal rho GH is proportional to the height. The density and G are all constant. So if the pressure is very high, it means you need very long piezometer. Just assuming in the barometer, whereby mercury rises to 0.76 meter, while water rises to 10.3. 10.3 is a very, long tube, very long one. Okay, so it means for higher pressures, means you need very, long piezometers. So that is why it is limited to very low pressures only. Okay, and we have this, which is example 7. Here it says for the closed tank with wooden tube, uh, gauges tapped into it, what is the specific gravity of the oil and the pressure reading on gauge C? So what's the specific gravity of the oil? Here we have air, oil, and water. We want to find the specific gravity of the oil and the pressure on gauge C. Pressure on gauge C is unknown. On gauge A and B are given. Okay, we want to find the specific gravity and the pressure on gauge C. So we start from known to unknown. Okay, at B we know the pressure. So let's find the pressure at B. Okay, we use the height of the oil and the height of the air column. Okay, the pressure due to the height of the air column, which is constant, okay, because it's air. We said it doesn't really vary with elevation, it's very negligible. So we use the pressure PA at the Bowden gauge here. Okay, so that's why we use it here, 50 kilopascal, plus the height of the oil column, 1 meter, with rho gh. So unit weight of water times 1 meter, and this will give us the pressure B at this point. Okay, so the only unknown is gamma oil, which we make it the subject of the formula. Okay, and it says specific gravity. This is the unit weight. The specific gravity is the unit weight of oil over unit weight of water. So unit weight of oil divided by unit weight of water. So the specific gravity of the oil is 0.87. You can see it's floating on water. So definitely our specific gravity should be less than 1. Definitely, if you get anything above 1, it means your calculation is wrong. So S is 0.87. Now to find P, the pressure at point reading, the pressure reading by gauge C. Okay, all we need to do, we know the pressure here. Okay, which is giving us, like the weight of all the fluid acting on this area. So we just add the pressure at B with the weight of oil 0.5 and the weight of water 1 meter. Simple. So PC is going to give us PB, which is this one, plus the pressure due to 0.5 meter of plus 1 meter of water. Simple. Okay, so pressure due to this, due to the oil 0.5 meter, and due to the height 1 meter height of water. Okay, plus the pressure at this point. The pressure at this point is PB. Okay, so when we add them up, we have 76.2 kilopascal, and that is it. Now we move to the next one, which is where I started my lecture from. The manometers. We looked at the barometer. We look at the, we look at the manometer. If you remember, we mentioned the pressure measurement. Look at the barometer. Okay, we look at the bull gauge, and we look at the piezometer. Now we'll go into manometer. Okay, which is the fourth one, which is where I started. Okay, and the manometer, we all have this, the pressure. We use it also for pressure measurement, which is a U-tube, measuring pressure by lowering arm. Remember, I explained all this. Pressure at the same point is the same. So we generate our equation for the right and the left arm and equate them to find whatever pressure that we want to find. Okay, here if we find P4, we equate the two, P2 equal P3 because they are the same elevation, and find P4. Okay, and this is the same thing. When you go up, the pressure decreases. When you go down, the pressure increases. Okay, and we say the unit weight of liquid is far, far greater than the unit weight of gas because of density. Gas density is far, far less than the density of liquids. Okay, and this is the piezometer's equation, okay, which we use the same principle as well. That is the fact that at the same elevation I and II, pressure at I is equal to the pressure at II. Okay, so when we find the pressure at I, which is equal to this, okay, I, and this is the pressure at II, we equate them, we arrive at this one. And we simplify using by dividing by gamma, we have it in form of the piezometric height of piezometric head, H1 and H2. Okay, so we were about to take this example when my time was up. Sorry, when I realized that I jumped some previous slides. Okay, so this is the example that I was about to take when I realized that I jumped some previous slides. Okay, and in this example, it is simply asking us, I mean, it's about the piezometric head for pipe flow. And you have a differential mercury manometer, which is connected to two pressure taps. Okay, differential mercury manometer connected to two pressure taps in an inclined pipe. And you have water flowing through the pipe. So the manometric liquid here is mercury. And the deflection of mercury in the manometer is 1 inch. So here we have delta H to be 1 inch, okay, which is the deflection of mercury. Find the change in piezometric pressure and pressure head between points 1 and 2. So we should find the change in piezometric pressure and the pressure head between points 1 and 2. So here we generate ideas. We should find two things: the difference in the piezometric head using equation 3.22 and relate piezometric head to piezometric pressure, okay, using the other equation. Don't forget this is the equation which we already derived, okay. It is the same figure. So the difference in piezometric head is H1 minus H2, okay, H1 minus H2, okay. So this is delta H. Yeah, it says 1 inch. 1 inch is 1 feet is 12 feet. Sorry, 1 feet, 1 foot is 12 inches. Okay, so 1 inch in foot is going to be 1 over 12, okay? And then we divide by the mercury unit weight and the water unit weight, okay, to get H1 minus H2, 1 feet, okay? And to get the piezometric pressure, we just simply multiply by the gamma of water, okay, which is 65.5 pound per square feet, okay, pound per square feet. Because of the time factor, I will stop here, okay, and then I will try to, this is 2-hour lecture, then I will try to cover another 1-hour lecture so that at least I will have a make-up for 1 week. Then maybe next week I will try to find another time to create another make-up class for the second week. Thank you.